Hey, what's up, guys? Chung here again. So this time, let's take a look at another LeetCode problem here. And 1406, stone game number 3, hard problem, hard problem. Okay, so Alice and Bob continue their game with piles of stones. They're like a, a list of stones. And Alice and Bob will take turns to select the first either 1, 2, or 3 stones. Basically, once it's one person's turn, this person can choose to take the first 1, 2, and 3 stones, and then it's next person's turn. It asks you to find the result here, right? So who's gonna win? So in the end, the person with the highest score will be the winner. And there also gonna be a possibility for both of the person end up with the same score, which in that case will be a tie here. Mm. This is like a classic minimum max uh, dynamic programming problem. If you guys have ever seen this kind of problem, but at least for me, this is the first time I ever saw this minimum and maximum problem. So how can you tell if this problem is a classic minimum or max problem? First, first has to be have two players, okay? Second what? Second, it has to be they have to take turns, right? Take turn. Third, third one is the also important one. Both have to play optimally, right? Play optimally. So with these three symptom or three details here, we can tell this is like a minimum and a maximum problem, right? So to solve this minimum and the maximum problem, so now we always use this kind of like a relative score, right? So basically basically every time when we add a new position here, we're gonna try to calculate the maximum the relative score for this current person because each of them uh, each of them will play optimally. So at this DPI here, it doesn't really matter. It doesn't really matter who is playing at this current position because any of them will try to play optimally, right? So then we can define this DPI. What's the DPI means? DPI means at the current position I, what's the maximum score, what's the relative maximum score that the current person can get, right? Um, maximum, right? Relative score. So to get the maximum, how many options this person have at this position I, right? 3, right? Basically, we're gonna have like the maximum of what? Maximum of, we have 3 here, right? Basically, this person can take either the first one, first 2, or first 3 stones here. So that's gonna be the sum of I to K, I plus K, right? I plus K. And since we're getting the relatively score, what it means is, okay, so now this person can take this three once after this person takes this K stone here, so the next we will give this game back to the other person, right? So what's the other person's maximum score, right? So the other person's maximum score will be starting from the DP I plus K, right? So that's and among all of them, we need to get the maximum. So this is the idea of the relative score because mm, this is the current person's score, and once this current person finish his turn, so DP it will start for this person basically from starting from this person will be the person starting and sorry. So for the other person, this A and B, right? So once player A is finished his turn, then this player B will be starting from I plus K, right? And then the best score for the person to start with B, so the what I'm saying, so the best score for person B to start at I plus K is in the D is in the DP I plus K here, right? With this information and the current one, we can get at at the current position I, what's the maximum relative score? Why we can use the maximum relative score, right? Because at this at each of the step here, this person this person I tries to maximize his winning score. Basically, this is the winning score, right? This is his score and minus the score the B can get, right? At this moment, the person A tries to get win at many scores as possible because he only has three options here, and he wants to know what's the maximum winning score I can win, right? So we just keep doing this from the end to the beginning, and once we reach the DP0, right? So once we reach the DP0, basically it means that at the position 0, what's the maximum relatively score, right? For this person A to start with. And in our case, it's the Alice, right? So once we have this DP0, we can simply use the value stores in this DP0 to tell us who wins the game, right? Because we're assuming this is basically the DP0 stores the for persons A, what's the maximum winning number for right to start as this DP0, right? And if this DP0 is greater than 0, then we know okay, Alice wins the game. And otherwise, if it's smaller than 0, then Bob wins. If it's equal to 0, then it's a tie. Right? Yep. Okay, cool. I think basically that's the concept of this DP minimum maximum problem. And let's get onto the coding here. So n equals to length stone value here, right? And then we're gonna have a DP equals to the system max size, right? Since we're going to get the maximum value for each of the DPI here, right? So that's why we need to have like a maximum value here, a minimum value as an initial state. And then so like I said, we're gonna start from the end, right? So range n minus one minus one minus one, okay? And then for DPI, right? So, okay, we're gonna have like a K, since the K is like a constant, 1, 2, 3, right? In 1, 2, and 3, okay? So DPI is equal to the maximum sum, right? The sum of stones, basically the stone value, right? From the I to I plus K, okay? And minus the relative, the other person's score, right? Which is the DP I plus K, right? And then in the end, we simply can return okay, we'll do the return later on. But the thing here is that since we're starting from the n minus one, right? From the n minus one here, we both the stone value and the DP value will be out of the boundaries, right? So we have two options here. You know, we can either do a check here, right? Basically, the stone value is this. This is fine, I think. And for DP here, we can simply do a DP I plus K if I is smaller than n minus K, n minus K, yeah, else 0, right? And because with these things here, if it's even though it's like out of the boundaries here, it will just automatically trim the sum here. If the I is smaller than n minus K, which in this case is going to be n minus K plus n. Okay, yeah. So once we have the DP here, right, we can just simply check return Alice, right? If DP 0 is greater than 0, else Bob, right? Bob, if DP 0 is less than 0, else Ty. Okay, I think this should just work. Oh, sorry, here it should be a sum of this range here. Okay. Stone. It's not iterable. Integer object is not iterable. Stone value. Oh, here. Okay. Yeah. So it works. And pass, even though it's not the fastest one, because maybe it's because we're keep calculating this sum here. Another way of doing this, like even though it's like constant 1, 2, 3, we can always still do a pre-sum so that it can speed up this sum process here, right? And another way of doing this thing is here, we can, instead of doing a check here, right, we can also do a padding here. of the DP and the stones here. We can do a paddings plus the 3 zeros in the end, right? Maybe same thing for the stones. But since this sum here, even though the I plus k exceeds the length, I believe the Python this like index slicing function will take care of it for us. So in case of other language, uh, if this sum, this indices is not will throw an exception. We can also do a like stone padding here, stone level padding plus right plus the also 3 indices here. Okay, 3 zeros here. So in that case, whatever the sum of the stones or the DPI will not affect our final result, right? So if we have this 3 paddings in the end, we can just simply do a DPIK here, right? And yeah, so we don't even need to care about the boundary stuff because we're making sure that it's always in within the boundaries. Okay, let's run it. Yeah. Mm, yeah, I believe that's pretty much it is about this problem, and it's just a classic minimum and a maximum DP problem. It shouldn't be that hard, but if you have never seen any of the minimum and maximum problem before, most likely you cannot solve this problem. But once you know what this minimum problem algorithm is, it's pretty straightforward. Basically, for the minimum and maximum problem, what you need to do, you need to get the maximum, since both of the players will be will will both play optimally, which means every time when either of them is at the position I, they will try to max their winning score. Basically, the winning score is the current score they can get, minus the the other the other person's score, right? And in the end, we just check the at the beginning, what's the score is look like, right? If it's a greater one, then it means the first person wins. Otherwise, second person, and if it's the same, if it's zero, then it's a tie. Okay, cool. I think that's it for this problem. Yeah, thank you so much for watching the videos and stay tuned. See you guys soon. Bye bye.